Good morning. We are now headed into a relatively new set of topics. This is chapter 7. We are looking at, I want to say first of all, energy. So energy is one of those really dangerous terms, and that's because everybody kind of has this idea of what energy is already, but physics has a very specific idea about what energy means. So we'll find that out in this chapter and the next chapter. So it's another one of those two chapter combinations. We're going to be looking at energy in a fair amount of detail in chapter 7 as well as in chapter 8. Now, work is related to energy. Work refers to a transfer of energy. Now, once we get a little ways into the chapter here, we're going to learn that there is something called kinetic energy. Kinetic energy refers to energy of motion. When an object is in motion, it has a certain amount, we say, of kinetic energy, and we'll see what the formulas are for that. Now, in this picture, here's a picture from the A's. And what's happening is that baseball right there, it's at rest. It doesn't have any kinetic energy. But by the time the pitcher lets go of that ball, it's going to have a fair amount. So the pitcher is actually going to transfer energy into that baseball. So by exerting a force, we can calculate how much energy is being transferred by measuring how much force is the ball being thrown with, and over what distance is that force acting. So if I can come up with those two measurements, those two numbers, I can calculate how much energy has been transferred. So here are the units of the chapter, and for these I'm going to stop maybe and take a little bit closer look at some of these. First of all, it's going to be looking at how much work, how much energy transfer is being done by a constant force. So in this previous example, what would happen if the pitcher exerted a constant force all the way through here? Well, a constant force times the displacement tells us how much energy has been transferred. If the force is not constant, we'll find that there are other techniques we can use to determine how much energy has been transferred in that situation. Now, along the way, we have to introduce a new mathematical technique. In fact, there's a couple new mathematical techniques we want to refer to in the chapter. One of these is taking a couple of vectors and combining them into what's called a scalar product, and we'll see what that means. And then we're going to move on and take a look at varying forces, forces that aren't constant, and what are the techniques there. This is going to involve using integrals, calculations from calculus. So, and don't panic, I mean, we'll develop all of the techniques that we need. It's not like you have to go back and review all of your calculus class, but we'll talk about some of the formulas and how to set up the integrals to carry out those calculations. And then finally what we've got is when we transfer energy, it's going to show up in most cases as kinetic energy, and we'll calculate how much kinetic energy that is. Now, at first, starting out, I want to recommend whenever you see the word work, say energy transfer. So I like to think of this as one of those funny English words where the spelling and the pronunciation don't match. How do you pronounce W-O-R-K? And this is pronounced energy transfer, because it's right there. Okay, to remind yourself what is going on here. All right, here's our first diagram to show how these energy transfers will take place. So here we've got this person, and they're what we call doing work. Now, work in physics involves exerting a force over a displacement. So here's a box. It's a big box this time. It looks like more than 10 kilograms. And we're pulling on that box, and what's happening as a result is the box is going to get pulled from here all the way over to here, and we're going to represent that as a displacement. So D, little d, stands for displacement, and that's going to keep track of how far the object has traveled. I think we said in this earlier picture that we started with, the displacement would be from the time the pitcher begins exerting a forward force on this baseball until the point where the baseball is released. So during that time the force is being exerted on the object, work is being continually transferred. Now the force that this person is pulling with is at an angle. I guess that's ergonomically the best thing to do here. But that means that there's going to be a force parallel to the displacement. There's going to be a component right in the direction of displacement, but there's also a component of the force being applied that is not in the direction of displacement. And what we find with energy transfer is that only the direction of force in the direction of displacement contributes to energy transfer. So that's why, in this case, they're saying the work or the energy transfer that's taking place is equal to the force times the cosine of theta. Only the cosine of theta factor applies here, times the distance. And so that's what's happening here. Okay, and we'll see this in other examples. This other force, which would be force cosine of theta, is not transferring any energy because it's perpendicular. And by transferring energy, for now what you can think of that as being is this component, is there a possibility that this component could speed the object up as it slides along the surface? And you go, yeah, that could speed something up. But if the object is sliding along the surface, this force is not going to be making it speed up or slow down. Now, there are other forces in this picture that we haven't included, and so let's take a look at those. There's a gravitational force. Now, the gravitational force is downwards, and at least in this example, the displacement is horizontal. So the gravitational force is not transferring energy in this example. There is a normal force, and the normal force is vertical. Now, if the normal force is vertical and the displacement is horizontal, that force is not transferring any energy either. So here's what I highly recommend everybody do in all their examples. When you're calculating work, put a subscript and say specifically which force are we considering. If we were to do that with gravity here, let's say we do the work, subscript mg, well, that's equal to 0. And if we did a work with subscript normal force, that's equal to 0. Now there's another force here that could also be doing work. What could that possibly be? And that would be friction. So there very likely is a frictional force opposing the displacement. So if you have force and displacement in the same direction, that's transferring work, that's transferring energy in, that work is. But if you have a force and a displacement is here, force is here. If they're in opposite directions, that force is actually taking energy out. So it's removing energy from the object. So friction could be taking energy out, this person could be putting energy in, and then we can do balancing. We can do a little bookkeeping to see how that the differences would show up. Here's another kind of interesting example with work. Here is somebody carrying groceries, and so they're walking with groceries and they're walking at a constant velocity. So here they are walking at constant velocity. Now, if the velocity is constant, then there is no net force in the forward direction. The person carrying the groceries would continue to have to exert an upward force, right, on the groceries, but they don't have to continually push forward at constant velocity. Now, if I'm starting at rest with my groceries, and then I begin to accelerate, if I accelerate forward, for that time that I'm accelerating, I need a forward force. But that might only be for a short period of time. So for most of the time, while this person's carrying the groceries, we can treat that as constant velocity, and there needn't be any forward force. So the force diagram only includes mg. Now what is this? Is this pull? I'm not sure what the P is for. I think of that as a normal force. So I got my arms under the groceries, and that's exerting an upward contact force in this direction, or I'll just call it F. So here's the force here, here's mg here. There are no forces in the direction of displacement. The displacement of the groceries is horizontal. There are no forces in that direction. That means no energy is being transferred in, and that means that there's no increase or decrease in kinetic energy, and that means the groceries just keep moving at the same speed. They don't need any more energy. They're not going any faster. They can just stay with whatever kinetic energy they have at the speed that they're traveling. So that's what this diagram is showing. Now, in this diagram, they have introduced energy units. If I take a force and multiply it by a displacement, the units that I'm going to have there are newtons times meters. And newtons times meters have a designation to them. Those are energy units, and they can be simplified and written as joules. So Joules. Joules are the units that we use to represent a certain amount of energy, or a certain amount of energy transfer. Ooh, here we go back to that crate again. So this looks like the first example. What we've got is the person pulling on this at 37 degrees, and the total displacement, wow, it's 40 meters. So it's not short. We've got a good distance here that this object needs to be pulled along that surface. So here's a more complete diagram now. I've got normal force, I've got mg, I have the displacement vector. Now that's not a force, that's a displacement. And that's written here as x. And then I've got the force that the person is pulling with. Now the numbers they give us here are 50 kilograms for the mass, 40 meters for the distance, a force of 100 newtons, which acts at 37 degrees. The floor is smooth, no frictional forces. And so we just want to go in and analyze the whole situation. Let's do that. So here's what we've got. I hope this diagram looks like the one before. We've got an F cosine theta component, and we have an F sine theta component. We have a normal force, we have an mg. They're saying for now, don't worry about friction. Everything is frictionless. Now, here's the mass. Here is the displacement, 40 meters. And here is the force we're pulling with. The angle is at 37 degrees. And so let's take the forces one at a time. The first thing I want to do, let's just eliminate some forces in terms of work. Here's the force N, mg, and F sine theta. And I'm saying the energy transferred by each of those is 0. And it's 0 because here is the displacement, this direction. Well, the normal force is not going to speed up that object. It's in the wrong direction. Displacement here is still in the x direction, but mg is still perpendicular. And then finally, F sine theta is perpendicular also to displacement. The only force on my list that's in the direction of displacement, or along the same direction, is F cosine theta. So what we can do is, now I think I took, out of habit, and that's what they were doing before, before they were calling this distance. So I've done that, 40 meters. So the energy that gets transferred by F cosine theta will be F cosine theta times D. F cosine theta and D line up in the very same direction. Now what I can do then is I can calculate how large is F cosine theta. And F cosine theta, that's 100 newtons, at 37, cosine of 37, ooh, I didn't get that redrawn. That's 80 newtons. So 80 newtons of force are in the direction of the displacement. The displacement was 40 meters. If I combine those together, multiply them, I'm going to get 3,200 joules. So that's the amount of energy that was transferred. And so that would be 3,200 newtons times meters. And we said newtons times meters is the same thing as a joule. And that's how we measure energy. Now, what does that mean for the box? And for the box, what that means is it's going to go faster. There was no friction force here. We looked at all of the forces. They said there was no friction taking energy out. All of that energy that was transferred in, this was 0, 0, 0, but this one was 3,200 joules. That is now what we call kinetic energy of the box. The box will be moving at some speed, and that's how much kinetic energy it will have. All right, lots of suggestions here for how to work these problems. A lot of the same things get repeated. So, but let's go back over the list. First of all, in calculating energy transfers, we want to go back and draw a free body diagram, which is our force diagram. So here is the free body diagram, and from that, I was able to provide a complete list of all the forces. And then I'll go through those one by one and identify which forces are transferring energy and how much, and which forces are just flat out not contributing. So that's the recommendation. And then choose a coordinate system. So that's been pretty common. We want a coordinate system where we can easily measure displacements. And then we can set up the force vectors so we can tell which components of which forces are transferring energy. Now, if we've got, they call these unknown forces, which I'm thinking of as probably something like friction. We haven't identified how much friction. We can use equations that we've been using in chapters 4 and 5 to figure out how much static friction or maybe kinetic friction that we have. And then list the forces and find out the, how do you pronounce this? This is pronounced energy transfer. So that's what we did, right? We listed each one of the forces, and then we took each one of the forces and drew a quick diagram to find out which ones would be transferring energy. We ruled out the first three forces and said, nope, the directions don't match. But finally, for F cosine theta, yes, we're going to get an energy transfer specifically due to that force. And then we went in and calculated. Now, to find the network, what we can do is add together all of the individual numbers. For this specific diagram, the network was 3,200 joules because that's the only force transferring energy. That would change if there were friction. What if friction were added into this diagram? Well, the frictional forces might be here. That would be kinetic friction. We could take the kinetic frictional force, multiply by the distance, and then subtract it. Because friction is in the opposite direction, that's going to be taking energy out. So in that case, we would have to subtract off any energy that friction transferred out. And when friction transfers energy out, it typically shows up as heat, thermal energy, which is kind of the random motion of molecules. So we're still making things move, or move faster, but in a random sort of fashion when we transfer energy through friction. All right, here's another one of these problems. Now these are helping to build kind of a conceptual understanding of how this works. Here's another, this is kind of like the groceries problem. So remember with the groceries, there was an upward force, and that's coming from the backpacker or the hiker. So there's this upward force on the backpack. We're specifically just focusing on the backpack right now. And there's a gravitational force. Well, neither one of those is climbing up the hill. Is that a hill? It's not very high. It's only, ooh, that's 10 meters. So if this is 10 meters, then, oh my gosh, we've got a 10 meter person climbing up that 10 meter hill. It's a giant. Anyway, so this could be much larger than what we have drawn here, certainly. But anyway, we don't have any forces that are guiding us up that direction. And you go, well, how can that happen? And it can happen if it's constant velocity. So a lot of these problems assume, yeah, they do at the end. So they do say that at the very end, after part A, B, and C. So you have to read the whole problem. A lot of times they'll assume the acceleration is 0. Now we don't have to do that. It's just the problems get to be more detailed if there are accelerations taking place. So, and as we'll find out in the end of this chapter and kind of into next chapter, it turns out in many situations it doesn't matter the specific path that was used in raising the backpack from here to here. It just depends on what the height was. All right, so it says determine the work. Ooh, that's actually energy transfer. A hiker would do on a 15 kilogram backpack, carrying up a hill of 10 meters, that's nothing. Determine also the work done by gravity during this time and the work done, net work done on the backpack. For simplicity, assume the motion is smooth. And okay, got it. So this time, let's take a look at the displacement. The displacement is at a constant velocity, but it's tipped upwards. So in this case, we have a couple of options. We could divide up the components of the force from the hiker and the mg, or we could divide up the displacement. We could say that that displacement, that vector representing displacement, represents a certain displacement horizontally in the x direction, and then a certain displacement vertically in the y direction. Okay, and that's, I think, the easiest or the easier way to approach this. I'm not sure that's the path they're going to take. Let's take a look and see. So here are the forces. The hiker is lifting up on the backpack. Gravity is lifting downwards. There's a displacement horizontally. Along the horizontal portion of the displacement, this force and gravity are not doing any work, but there's a vertical displacement that we've got to go in and take into account. So in this case, what I'm going to do is take the angle between the force and the displacement. Notice where the angle is. And so if the angle is here, then the energy transferred by force F would be equal to F times d cosine theta. If I take a look at what d cosine theta is, it's h. So in this case, the vertical displacement is h. And I can substitute that in and say that the energy transfer due to force F is equal to force times h. And we could just leave it there for a second and talk about that. Now, the other item, though, that we want to ask about is, well, how big is force F? Does force F need to be bigger than mg? Or does it need to match mg? Or could it be smaller than mg? Now, if we imagine constant velocity and no acceleration, then what's happening is force F exactly matches mg. It doesn't have to be bigger. It needs to be at least as large in order to have the backpack, well, on average, let's just use the constant velocity argument and say that F needs to be equal to mg. Now mg we can calculate from m and g, and it works out to be 147 newtons. So that says that the force of the backpacker on the backpack needs to be a steady 147 newtons. Now the height, which is the vertical displacement, that's 10 meters, so there you go. The work done by force F, the energy transferred by force F, is 1,470 joules. And that was only 10 meters. It's not like the hiker went on and on and on for a long distance. It could have been 1,000 meters, right? Something more like that would have been more impressive. Now, what about gravity? Now, there's a couple ways of looking at gravity. And here's my favorite. I would say gravity is in this direction. Which direction was the displacement in? Well, there was a horizontal component. Gravity did not contribute to that. But there was a vertical component, and gravity opposed the vertical displacement. So I would put a minus sign in and say gravity, did kind of the same thing that gravity has the same force, excuse me, as force F. It's 147 newtons. And the angle between gravity and the displacement is here. So I could think in terms of this angle if I wanted, or I could just put the minus sign in by hand. And I think that's easier. Now I went ahead and did the math. I said that this angle right here between displacement and gravity, that is 180 degrees minus theta. And so I took the cosine of that and multiplied by mgd, and that automatically gave me a minus sign. Again, I think conceptually the easier way to think about this is to say mg is 147 newtons, the displacement is 10 newtons, and they're in opposite directions. So force times displacement, and then add the minus sign by hand. And we end up with minus 1470 joules. Now in the next chapter, we're going to start calling this gravitational potential energy, and we call it potential energy whenever an object is moved into a location where the energy, we could get the energy back. When we lift something through a gravitational field, right? Something goes up through a gravitational field, we can lift it up, it's got more potential energy, and then we lower it, it's got less. If we let go of it, that potential energy becomes kinetic. Now that's getting a little bit ahead of ourselves, but that's where we're headed with this. So the hiker transferred 1,470 joules in, gravity took out 1,470 joules, the net energy transfer is 0. Now that's saying that the velocity will remain constant. What would happen if the velocity were increasing? What if the object ends up traveling faster and faster? Well, that would mean that the hiker has to run faster and faster, right? And if the hiker did that, then the work transferred would end up being larger. The force of the hiker would be bigger than mg. There would be an acceleration. The energy transfer from force F would be larger than the energy taken out by gravity. And at the top, the energy transfer net, W net, would be a positive number. And that would mean that the backpack is going faster than what it started out. So that's how all these designations work. Okay, so here's a little more detail on that, and I guess it's the same stuff I talked about. So here is the diagram. Here is dividing up the so this is really outlining all of those recommendations. here is d sine theta, here is d cosine theta. I've got the energy transfer due to force F is F times the displacement in that direction. That's 147 newtons times 10 meters, and multiplying those together gives me 1470 joules. That's addition of energy. Now for the force mg, that has a minus sign on it because it's directly opposite to d cosine theta. So I'm still using the d cosine theta. I've got a different force, but it has a minus sign attached. That becomes 1470. That's energy being taken out. So transfer energy in, transfer energy out. What about circular motion? Now we've just, a couple chapters back, we had started looking at circular motion as an example. And so here is the moon orbiting the Earth, and we're going to treat that as perfectly circular. And so if it's perfectly circular, then the displacement, the instantaneous displacement, is always perpendicular to the instantaneous gravitational force. That means that this force is not speeding up the object, it's not slowing it down, it's redirecting it. If you remember, a sideways force redirects the velocity but doesn't change how fast the object is moving. So that gravitational force is not transferring any energy. Transferring energy would result in the moon going faster and faster, or slower and slower if you're transferring energy out. But if we're going to maintain a nice steady circular orbit, then there is no energy being transferred in by a perpendicular force. So that's kind of interesting to realize that that's a significant force. So in terms of force, there's a very real force there, having a very real effect. The moon is not going in a straight line, it's going in a circular orbit. But there's no energy transfer involved. Okay, so energy transfer is more than... and again, this is a diagram showing, if I think in terms of displacements, as I travel around the circle, there's a series of these infinitesimal displacements. I'm going to represent those as ds. That's what is a very common notation in calculus. Not sure what notation you guys are more familiar with, but I'm going to go ahead and call that ds. The ds is perpendicular to mg at each point, and so there is never any energy transfer that takes place for circular motion. So the centripetal force in general does not transfer energy. All right, now mathematically what we've been seeing here is we keep seeing these cosine theta factors show up. What we keep seeing is, if I take a vector, which might be, let's say this is force, this A vector, and then B is a displacement. Well, we can generalize this for any two vectors. And what we define is something we call the scalar product. If I take vector A and combine it with that vector B in a manner where I'm taking AB cosine of theta. So I take whatever the magnitude of A is and whatever the magnitude of B is and multiply it by the cosine of the angle between them, I end up with this scalar product. And so that's what this is saying. Here is energy transfer. We can write that in the new notation. Now what that represents, this AB cosine theta stuff, is here's any two vectors. They're separated by an angle theta. I can take one of the vectors and take its cosine theta component, and then take the cosine theta component and multiply it by the other vector. Now I can reverse this. So I could take vector B and divide that into components. It's going to have the same cosine theta. So it works either way. A dot B is equal to B dot A, where dot means carry out one of these scalar products. Okay. So anyway, that's what these dot products represent. It's compact notation that we can use for these examples. All right, so here we got a person. This person is pulling along a wagon. So there's a wagon. The displacement's going to be here. It looks a lot like, what was the, dragging that box, right? So now we're dragging a wagon, and we're going to have a force in some direction, and that force can be divided into components. So I can divide that up into components of x and components y, and it looks like the horizontal components will transfer energy, but the vertical components will not. The angle here is 30 degrees. I've run into trouble, you guys know this from an earlier lecture, that I've been running into troubles with the angles. They keep switching them. They switch them back and forth between 30 degrees and 37, and sometimes I'm using the wrong angle. I apologize for that. But that always gives you guys a chance to go back and I guess, double check the work. Let's see, so this time we're pulling with this person is pulling with 20 newtons at 30 degrees. Calculate the energy transfer and use the dot product when the wagon is dragged 100 meters. I think it's being rolled or something, right? The wheels are spinning. Anyway, ooh, look. I wrote this as a dot product. So I think that's what they wanted us to do, is just practice that. It is a little scary. So here is the energy transfer. And now what I can write is force vector with a little vector sign over the top, and the displacement vector with a little vector sign over the top. And then I put a dot in the middle, and that makes it a dot product. And what that stands for is the force, which is 20 newtons, times d, which is 100 meters, times the angle between them, which is 30 degrees. And what we found is the angle can either be thought of as a component of d or a component of f. It doesn't matter which approach we take. Now the cosine of 30 is 0.866. It was 30 degrees, I think. And so the energy transfer, now this should have a little f down here. I need to do that, write that in. So the energy transfer due to force F is 1,732 joules. And the problem gave us a chance to go in and write this as a scalar product or a dot product. Now the reason it's called a scalar product is because I start out with two vectors, but what I'm calculating is a scalar. Okay? It's not a vector anymore when I get through, it's just a number. Energy is a scalar. Energy is not a vector. Energy does not have directionality to it. Energy does not have x, y, and z components to it. So that's it, I guess, of what I want to state for this. Now, if we have an object, let's imagine, up until now, what we've been looking at are constant forces over a displacement. But what we could move on to is, and ask about is, what happens in a more general situation? What happens if I have an object and it moves a short distance here, and then it moves a distance, and it moves a distance, and here, and here, and here, and here. So what happens when I have a series of displacements, and they're kind of curvy? So the displacements aren't all lined up neatly like they were before. And then what happens if the force that I'm applying also changes direction? Like this is force at location 1, with angle theta 1, but this is force 2, 3, 4, 5, 6, 7, and each one of these angles differs. Now they've only indicated a few of these, but you can kind of fill in force 2, force 3, force 4. You could draw in theta 2, theta 3, theta 4. If the force is varying and the direction of the displacement is varying, I would have to do this one step at a time. I would have to calculate the energy transfers for force 1 over displacement 1, add that to force 2 over displacement 2, add that to force 3 over, and so on. Now, this can't be the only force acting on this object, because the forces listed here would not lead to this object following the path that they've shown us. So this is a very general diagram, and what we find we can do is this. If we take each one of these displacements, now they have broken up the displacements such that they're all equal distance, that's fine, and they're using for this delta L, that's fine. And then what you can do is you could take F1 cosine theta 1, F2 cosine theta 2, F3 cosine theta 3. Here is F5 cosine theta 5. Each of those are going to be a little bit different, but we can add them all together. And you guys are probably noticing we're setting this up to become an integration problem for energy transfer. So what we can say is that the energy transferred then, now they're using an approximation sign because right now they're taking small steps, but they're not yet in the limit of infinitesimal size steps. And so it's not quite this function the boxes, the rectangular boxes, don't quite match up with the function. But if we take shorter and shorter steps, then eventually it will match the curve. And that's the definition of an integration. So what we've done is we started out with this summation, adding up a series of finite steps. In the limit, where the step size goes to 0, that can be rewritten as, here is the force. Now the force could be variable. It's inside an integration sign. Here is the angle. The angle could be variable. It's inside the integration sign. And here are the little steps. Now they've written the steps as dl. If you remember, I wrote the steps as ds. It's not a big deal. But I'm probably going to use ds more commonly. Something to be aware of, that my notation might be just a bit different. So here is the formula, and they've highlighted it. That formula will work if the force is varying. So we don't need the force to remain constant anymore. We just need some kind of a function that tells us how the force is varying as a function of distance, not in terms of time, but in terms of distance. So at this step, how much force was there? At this step, how much force was there? At this step, how much force was there? We can carry out the integration. And what that will give us, if you guys remember from your calculus classes, that's going to give us the area under the curve. The energy transfer, the work, is the area under the curve of an F versus displacement graph. It's got to be force versus displacement. If those are the axes, and we've carefully plotted this out, then that's going to tell us how much energy is transferred. Okay, so an example here that we are going to start with of a variable force is what we call an ideal spring. Now, an ideal spring behaves this way, and we're going to see these ideal springs. They're going to stay with us. The ideal spring represents any mechanical system that has some flexibility to it. So a material that can be compressed or it can be stretched out, and we're going to find it can also be used to store energy. So those are the things that we're watching for here. And here is a spring that is unstretched. We call that its natural length. Now, I've got this attached to a wall, and that's to kind of simplify the diagrams. I've attached this to the wall, and then in this lower diagram, I've pulled that outwards. Now, the force exerted by this spring is given by the force of the spring is equal to K times X. Now, the minus signs can be useful. Sometimes we need the minus signs there in our formulas. Other times we can suppress those. We don't necessarily need the minus sign there all the time. What the minus sign is telling us is this. When I come back to the natural length of the spring, I set up a coordinate system where right at that unstretched length, x is equal to 0. Now what that tells me is that when I pull on this, x is, let's say it's going positive, it was 0, now it's some number, and let's call this the positive direction. Well, the force that the spring is now exerting on my hand is in the opposite direction to x. So in that sense, the minus sign is keeping track of the idea that the restoring force for this spring, the spring tends to restore itself back to equilibrium, will always be opposite the direction that the spring has been stretched. If the spring is stretched in what we've called the positive direction, then the force will be in the negative direction. If we compress this ideal spring, and if we call this direction negative x, then the force is in the opposite direction. So another item to keep track of here is little k is referred to as a spring constant or a force constant. Now it's going to be different for each spring. Each spring in general will have its own spring constant. The units on a spring constant or a force constant are newtons per meter. So that's what those units will look like. Now notice that when we slowly stretch out this spring or we slowly compress it, as we move the spring out or as we move it back, and I guess it doesn't, right now it doesn't have to be fast or slow, it could be either one. The force that we pull with balances the force of the spring. So when we say that the force is equal to, I'm going to drop the minus sign, if we say we have forces with a magnitude of kx, well, that gives us an idea of how hard we have to pull, and it gives us an idea of how much force the spring will exert on us. So again, sometimes we'll want the minus sign there, other times we don't need it there. We'll leave it out, we'll suppress it from the formulas. All right, now how much energy is involved in stretching out the spring or in compressing it? And this is where we want to pay close attention. Did I go back? I did. Okay, I did. So here's the math behind it. And so here is the force that we are pulling with. And so notice they've dropped the minus sign. They're saying this is how we are transferring energy into the spring. And in fact, let's go back and take a look at that. Which one of these pictures represents transferring energy into the spring? So the lower pictures, both of them, when we stretch the spring out, that's transferring energy in, and we can see that because the force that we're pulling with is in the same direction as the displacement. Now that force and the displacement are in the same direction, and that means energy is being transferred into the spring. Now in this case, the spring is not going faster and faster. The spring is actually storing the energy. So in this case, the work, the energy transfer that's taking place, is showing up as potential energy stored in the spring. So at this point, I have stored energy in the spring, and I can calculate how much energy has been stored by taking the force I'm pulling with and multiplying it by the displacement. If I compress this, the same thing happens. What happens is I push on this, and the force I'm applying and the displacement, they're in the same direction. I'm transferring energy in. So this represents stored energy, and this represents stored energy, and stored energy is called potential energy. Here's the calculation. So what we're going to do here is plot the force as a function of displacement. So here is the force, here is the displacement, and as we had noted, they've dropped the minus sign because now this is how much force we are applying. And when we plot this, the force, it gets harder and harder to compress the spring. It's getting harder and harder to stretch out the spring. When we carry out the integration becomes force, which is kx, integrated over a whole series of dx's. And integrating that becomes 1/2 kx squared, evaluated between 0 and x, gives us a formula of 1/2 kx squared. So 1/2 kx squared represents the energy that we have transferred into the spring. And if it's an ideal spring, all that energy is still stored. So that also represents the potential energy stored in the spring. Now we had said that the area under the curve will tell us how much energy has transferred, and the formula for a right triangle would be 1/2 height times base. 1/2 kx times x is 1/2 kx squared. So that's where the 1/2 is coming from, is because at first we didn't have to push very hard to get the spring to compress, and as we pushed harder, well, as we stretched the spring more, that required a larger and larger force. Okay, I think we're at break time, so I'm going to stop there. If you guys have questions, let me know. Right away is fine, and after the break we'll be back.